Okay, hi. So this is the week 6, and we today will discuss about Word2Vec, and uh, so this part it is lecture from CS 124 from Stanford. The first part will contain many like philosophical things or linguistic things, which we will also see, but we'll skip some of them. So if you do not want, you can not read it. But after some time, it will go to real like Word2Vec about vectors, how to represent word in vector form. So the what the words mean. This is like first of look in dictionary. So we can think what does words mean. So they may mean many different things. Like for example, it is lemma. It's like root sense. So for one word pepper, there can be 3 4 senses and definitions and etc. So the many times the most of words have several meanings. So even like if you think it is one meaning, it may have different meanings. For example, in some industries may have mean some other meanings, etc. So for pepper we have 5 senses. So it may be spice from pepper plant. So you made spice, so you can ask spice. So it can be the plant itself. So it's something totally different. So it is something that's added to meal, but this one is some. It can be considered as some plant, another similar plant. So there can be two plants. Also, there can be third plant. So there are 3 plants and they are different. So for example, from the point of view of uh, some botanics, it can be different. Sense or concept is the meaning component of the word. There are relations between senses. Again, so there is if you remember, there are things like synonymy. So each word has its own synonyms, like coach, sofa, big, large, etc. So they may be different in some cases, but maybe similar. In some cases they may be similar. In some cases they may be different. So for example, water H2O. So for example, if you are reading some uh, chemical chemical some paper or article about chemistry, uh, you can see this one, but most of the time you will see something like water and etc. Still may not proceed based on notions of politeness, slang. So sometimes it based on politeness, slang, register, genre. So it's can be different in different. So even they may be same, but in some cases they may be different. Uh, Big, large, brave, courageous. Okay, there's some. So. Uh, so for example, not synonyms, but for example, car, bicycle, they are not synonyms. They are not same things, but they share some common things. Like cow, horse, it's domestic animals. Car, bicycle, it's some like transportation vehicle. And by using this, we can see what to do. Ask humans how similar two words are: vanish, disappear, behave. So we can ask humans and say what is the similarity. So it is out of 10. So the people say vanish, disappear, they mostly similar. For example, behave, obey, they similar in 73. So they people give some points for each this: muscle bone, modest, flexible, whole, agreement, etc. So this is totally different, but someone have given some points to it. Word lateness also got word association. So car, bicycle, similar. Car, gasoline, related, not similar. So gasoline and car, they are mostly like related, etc. semantic field. So for hospitals, you can see these words: scalpel, nurse, anesthetic, hospital, houses, durif, etc. Antonymy is also from linguistics. You know that they think that opposite, like this one, superordinate or subordinate. So, for example, car is subordinate of vehicle, so subset of vehicle. Mango is a subset of fruit. So, mango is a fruit, and but not all mangoes are fruits, but not all fruits are not mangoes. So, this is also some understanding. So this part is about how to understand the meaning of words. Will not stop on these things because they are quite specific. Actually, not this one. So because the main principles we know. So for example, this is for words cup, bowl, and people try to understand what is called cup and what's called bowl, and they say, okay, percentage of when and how these things are called cup or bowl. So this is diameter. So bowl is like in Russian tarelka. Cup is krushka. So as you can see, they are same things, but differ on like what you eat from that, and what is the size and relative size of it. So this is people try to. We will pass it. So we will try to try to create new understanding of word. Each word is a vector. Now just word or word 45. Similar words are nearby in space. So we want to make something like this. So for example, this is like location on some space. If you remember linear algebra, this is some number. So for example, it can be 10, comma 7, for example, and this is for example 9, comma 6. So we have some words, and each word is considered as vector. And by using these vectors, you can understand that, for example, very good is very near to amazing, and you can do something with this information. You can try to work. We define word as vector, called an embodying because it's embedded in space. The standard way to represent meaning in LP. Okay. So, for example, sentiment analysis, you can find out the words in some. You want to find it, and you want, for example, you want to find sentiment like positive or negative. To do this one, you can find, for example, the previous word was terrible. Requires same word to be training in test. So you can train, for example, on word. In train, you can find the word terrible, and you can find if it is like negative. And after that, you can find from this vector space, the word which is near to terrible, like it was here, terrific. And in training, you find that terrible is here, and in test set, you'll find some other word like terrific, and you will see, okay, they are very near. So this means that if this one is negative, so this also will be negative. So the intuition is something like this. So for example, when you train on data, you find some words, and by these words you find some logic, but after that you can use these vectors. So two kinds of embeddings, TF-IDF. TF-IDF, I explained it before. So it's common baseline model, so it's like standard. Sparse vectors. The word sparse means that it is all mostly empty. Mostly it has zeros, meaning that it will contain mostly zeros.
and it is very big. If you want to multiply them, it will take a big amount of time, so it is very hard to do this one. Words are represented by counts of nearby words. So we have word2vec dense vectors. Representation is created by training a classifier to predict whether a word is likely to appear nearby. So we have something which is called word2vec. It is dense vector. Dense vectors means that most of its value is not zeros, and is sparse vectors. Your vector will have size, for example, 10,000 or 100,000. But in word2vec, you have much dense vectors, and it's mostly smaller, and it is also contains much more information. Okay, so this is term document matrix. As you remember, this is, for example, this is some document. It was as you like it, and it contains bottle one time, good 140, font 14, full 36, width 20. And so for each document we have something. And we can also use this one for different purposes. So if you visualize it, for example, Julius battle and full. Battle is used in Henry 4. Okay. So this is the number of words. So for example, Henry used battle 13 times and full 4 times. So by using it, you can actually find that these two documents are very similar. So for example, we can do like this one. So these are two similar. Comedies have more fulls and width and fewer battles. Words can be vectors too. Word matrix. Cherry. Okay. So we can also make so this one is quite different word to word. So you say that how many times computer occur near digital, I think. Okay, so we have, for example, this word digital here, and here digital, and we have computer. So this number is how many times the word digital occur in same sentence or same document, how many times. So we can create something like this, and also we can use it as some vector. So for example, computer and digital was used this amount of times together, and this information in this amount of times. And we can use cosine for computing word similarity. We didn't use it, but I also passed it before and explained. So for example, to find you can use Euclidean distance. Euclidean distance is distance between this and these points, while cosine distance is when you count this angle. So it gives the number between 0 and 1, as I remember. Yes, 0 and 1. 0 means that they are similar, 1 means they are not similar, they are mostly like controversial to each other. Plus minus 1 vectors points in opposite directions, plus 1 vectors point in same directions. So here's some formula. So for example, cosine between cherry information, and you have this word-to-word data, which shows that, for example, cherry and pi occur together 442 times, cherry and data 8 times, computer 2 times. And you can find the distance between cherry and information. So for example, this one and this one. So this is actually like this one, cherry and digital. Cherry cosine distance between like this, and this one is distance between digital and information. So it means that digital information are very near to each other. But row frequency is a better representation. So this one is row frequency, this one. Frequency is clearly useful, so if sugar appears a lot near apricot, that's useful information. But overly frequent words like the, it, or they
they are not very informed about the context, need a function that resolves this frequency paradox. So there are two things, like if two words appear together, they are like that means something. While if two words are, but there are many words like they, it or they are not together. Many functions help in reweighting the counts, for example TF, IDF, or pointwise mutual information, which makes it better. So we have TF, IDF vectors. They are long. They have lengths of documents or vocabulary. It's very big. So we have vocabulary, for example, for many languages. The most used information, they will be like hundreds of thousands of information. So 100k. So for example, like this one, they removed some of words and something. Sparse, most elements are zero, so they are zero. But we want something different that will be short, very short, like this one. And dense. Most elements are non-zero because these ones are stores many. If you want to store them, it will take much memory, so you have to store them. Short vectors might be easier to use as a features in machine learning. Dense vectors may generalize better than storing. So in machine learning, dense vectors are better, and the dense and short vectors are better because in some rare words they may have like mostly zeros, and for example, if you want to try to find the different synonymous, it would be harder. So there are two common methods: neural language model and singular vector decomposition. Singular value decomposition is quite old method. It uses matrix multiplications. Sometimes it can be used, but mostly now uses neural language model. So this is person who created it first version, or maybe there was some researchers before, but first, like, this name for TUVEC was presented by Mikolov, Thomas Mikolov, who created it and implemented. And also after that it has GloF. Also there is fast text, which is some improvements of this word TUVEC method. Very fast to train, code available in that. The idea predict rather count. So this is called generative. Instead of counting how often each word occurs near apricot, Transi classifier on binary prediction task is V likely to show up near to okay. So we want to predict something. So for example, we have word target, and I want to make this apricot, and we have window word, so plus minus 2, so it means that two words, two things to this part and two to this part. And I want to say that apricot, I want to predict if the word tablespoon can be near apricot, and or if jam can be near apricot. So we want to something like this. We want to predict, we want to enter word apricot and to predict if jam can be near to it. So for example, it can be like this one. Like you say apricot, and here it will have some black box, and then okay, and then here we have jam tablespoon, And here, for example, what cannot be near apricot? Anesthetic, for example. So it's something like this. You say jam near word apricot. What's the probability of that jam will be near? So for example, here we write 0.8 tablespoon, 0.5. So for example, sometimes and anesthetic 0.001. Let's say something like this. So the task is something like this. I say, okay, I will give apricot, and what you output all the words, and output if it is possible that it will be near of this word in the direction of two words. So I give some values. So because and skip that training, you give positive examples like target is apricot and C is tablespoon of jam and etc. So this is like positive when it was positive. And then you give K negative example. You will have to create new negative examples. So it will be like you will have to find all apricot words that are near and remove them from vocabulary and randomly select from vocabulary any words that are not that never happened near apricot, and you can create some. For example, apricot, advark, apricot my, apricot where, apricot coaxial, apricot 7, apricot forever, apricot dear, apricot if, etc. So this is called negative sampling. You create some negative examples. We need negative examples because it will learn on these ones, but it will also, must also learn on some negative examples. And then we specify here the words, for example, 3 Raxen. Okay, so are there any? Okay, so this is something like this. You have vocabulary and you use neural network. Okay, so let me draw it. Okay, let me draw. So it is something like this. You have input here, which contains, for example, 10,000 examples. 10,000 examples, not examples, but words. Words, and so this is 10,000 vector, and one of them, at this point, like 1,568 is word apricot. So this part is all words, like all of them are 0, only one is 1. Now you have 300 neural networks, neural nodes, and all of them is connected, and then you output same result for 10,000 words. So in this part 10,000 words, but mostly it contains zeros, like 0, 0, 0, 1, 0, 0, 0. But when you use this neural network, it must output some probabilities. So for example, first word is aardvark. If you are interested, it is muraviet in Russian. So aardvark is 0. For example, 001. So you have 10,000 words, and each of them will have some value, and you try to generate all of this word to vec, and in the middle we will have this these neurons. It will be about, for example, 300 neurons. So how it is trained? You give these words, they are like trained, and these values change. You try to predict this one. After you finish, you will have these 300 neurons. It will be like you can also consider them as a vector. So for example, when you write apricot, you multiply these weights and these neurons give some results. So actually, in Word2Vec, you take these neurons. So actually, you are training on this part all of these trainings. All you use this whole neural network. But in the end, when you need Word2Vec, you will take only this part, these vectors, and for example, you write apricot and it multiplies. Actually, not multiplies, it stores, and because it has many zeros and ones, so it will only take only one weights, and this is one is Word2Vec. So by using this neural network, you create some data set, data. So and you write the index of your word, and it gives you some vector. And this vector creates something very interesting thing, like this one. So, for example, from word Hogwarts, nearest neighbors are Dumbledore, Half-Blood, Malfoy, because they are like similar to each other. Hogwarts near neighbors is okay, it's the same. And also this showed us very interesting things, like the word woman was near to word man in this direction. So it is in glove. So you see that woman in similar direction from man as madame and sir, queen and king, empress and emperor, countess and earl, duchess and duke, niece and nephew. So the word, this Word2Vec algorithm is actually created some. It found out that they have some meanings, and for example, woman is we can consider that woman is aunt and uncle is man. So this was very important, like very significant change of components. You can use Paris minus France plus Italy, it gives Rome. Also, it can give a cultural bias. For example, Paris, France, Tokyo, Japan. Actually, it's not Japan, but Kyoto. Father, doctor, mother, nurse. So, for example, it's like mother cannot be doctor, something like this. Man, computer, programmer, woman, homemaker, and something like this.